Hi, I'm Joe Stankiewicz. I'm here today to talk to you about the O3DE scene pipeline. Start with an introduction of who I am, give you a walkthrough of the scene pipeline, go over scene settings that let you control how your scene files get brought into the engine, and finally, options for automating workflows to save content creators on your team time getting those scene files set up in the engine the way they want. I'll have some documentation links on the final slide. I'm a software development engineer with Amazon Web Services with 17 years of game development experience, and I have a focus on tools and asset pipelines. The first thing to know about the O3DE scene pipeline is the asset pipeline. This is a modular toolchain that converts portable content to the game-ready assets that you place in the editor or prefabs. The asset processor lives at the center of this. It converts files like the scene file filmbox FBX files to the game ready content, the models and materials that you'll interact with in the editor to represent that 3D content. We call that first step a source asset, the portable assets, the assets that are usable elsewhere. And then the engine specific content we call product assets. The big difference here is the product assets are going to be read only. You shouldn't make any changes to them because the next time the asset processor runs, it may overwrite those changes. I also want to briefly mention the starting point for content creators is often going to be an external tool, a digital content creation tool, or a DCC tool for short. The three most common ones we've seen with O3DE are Blender, Autodesk 3D Studio Max, and Autodesk Maya. One of the first things people need to understand about the scene pipeline is what scene files actually are. And the simple answer will suffice in most cases. The scene file is just a file that contains the 3D content for your game. But to understand the detail we're going over later, it's important to know that in most cases, a scene file is actually going to be a node graph with nodes that represent the 3D geometry, the materials, the animation, and other information for your scene. And it's done this way because it lets the elements have a hierarchical relationship. One of the first things anybody asks us is going to be, what formats of scene files do you support? It's important to know because you need your files in that format to get them into the engine. And we support primarily Filmbox FBX files. This is a format maintained by Autodesk. And specifically, we support them in the range from 2011 to 2013, the best, as well as from Autodesk Maya, Autodesk 3D Studio Max, and Blender are some of our most tested digital content creation tools for generating those files. The difference between our support for Maya versus Max and Blender for FBX comes in the form of physically based rendering material properties. Each of these tools has extended the FBX format in a unique way to add physically based rendering materials. And so far, we've built that support out for Maya because it was the most requested. If you want to see physically based rendered material properties come in from other digital content creation tools, reach out on Discord or GitHub, and we can talk about what it will take to make that happen. Next, I want to talk about what we partially support. For FBX, partially support means there may be some known issues. The FBX format is proprietary, so a lot of other tools like Blender have reverse engineered it. The Blender team has a great blog post where they go over how they reverse engineered the FBX format. As well as the FBX format often has specific extensions from those tools, like I covered with PBR materials. So from other, we best support it from those three digital content creation tools, Max, Maya, and Blender, but we do support it from other tools. You just may run into some gotchas. We also support graphic language transmission format files, a GLTF and GLB. GLTF is the text and GLB is the binary. And we support STL file. STL is an older format and it doesn't really have a definition. It has a few backronyms, standard triangle language, standard tessellation language. We mostly supported STL as a simple format to help us test extending the engine to support additional formats. Which brings me to our experimental support. We use an external library called the Open Asset Importer Library to do a lot of the heavy lifting of loading those scene files off disk and into memory to be used by our pipeline. And the Open Asset Importer Library supports an even wider list of formats than I've gone over already. For example, we've seen some external contributors turn on Collada format files for themselves. These are experimental because there may be some known issues. We might not have any automated tests in place. So There shouldn't be anything stopping you from turning it on locally, trying it out, but be aware you may run into some challenges. And if you do, reach out on Discord or GitHub, and we can talk through those. The last thing I want to cover before I move on to the scene pipeline is the actual data we export. So far we've covered we load the scene file, we get that data in, but the product assets we put out that can be used by the rest of the engine include the static geometry, like you see here with the shader ball. We also support skinned skeletal characters and animations just for skeletal characters. We don't support animations for skinned meshes. Animations can be done through either standard skin mesh animation or morph target animation. Morph target you may also know as blend shapes. This morph targets and blend shapes are generally used to animate faces for characters. If you need to animate a non-character, you can create a skeleton for your static geometry and animate it that way. That's what we've been doing with a lot of our robotics tests. The next set of scene data we output is physics, and physics is interesting because that scene format I described earlier, you've got a node graph where it'll have a node that represents geometry, a node that represents a transform. There's not really a concept of physics there. Instead, our engine figures out what it should use and create for a physics product asset based on information in the scene file itself, such as the name of a node or the scene settings that get loaded and applied to the scene file, which we'll go over in detail later. The other set of data I want to briefly cover are the indirect data. This is information that's used by the other files to make them able to reuse or share data across different files. So like an AZ buffer and an AZ lot is used by an AZ model. The skin meta file is used by the skin character. It's something you shouldn't really have to think about or worry about. I'm mentioning it though because you will see that as output when you look at the output of your scene file in tools like the asset processor. And the last set of scene data I want to talk about, and this is the most exciting to me, it's something that we spent a lot of time building last year and this year, is support for prefabs from the scene system. A lot of the time, your content creators working in these scene files in Blender, Max, or Maya, and they want to recreate a scene with a similar hierarchy in the engine because they want to be able to position or move objects relative to each other. A common example we like to use is a car. You might have a car body node, 4 car tire nodes. You don't want those welded into a single mesh in the engine. You would prefer to have each of those tires come in as a single entity in the engine that can be rotated independently of the car body. And this is what procedural prefabs enable. The default procedural prefab, which you see I've shown here with the Sponza scene that comes with the automated testing project, gives you a entity per node that had a static mesh. We don't have any default procedural prefab information for characters yet. If it's something you'd want to see, reach out on Discord, talk to us on GitHub. We also have support for custom procedural prefabs. This is one of the options your technical artist will have on your team to save your content creators time. If you're finding that you're creating a similar entity stack for similar FBX files, similar scene files as you are building your project, then you can use the custom procedural prefab system to automate those steps for you. Create the entities based on information from the scene graph and put them into the scene with any game-specific components on them. Now that I've covered what scene files are and what product assets are generated from them so that you can use in the editor to build your project, next I want to go into details on how these files are actually processed into those product assets. First, I want to do a little bit of a closer look at the scene pipeline. You'll notice a couple new steps here. The first is a file that's proprietary to the digital content creation tool. In this example, you'll see the Blender tool uses the blend file, but this is true of almost any content creation tool for making 3D content. The content creators are going to want to load and do most of their work out of a file that's built to work with that tool. The upside here is it contains a lot of extra information that lets them get the content created faster. The reason why this is important is if you wanted to make any changes to the scene file, to the FBX file, this pipeline is one directional for most teams. So if you change the FBX file as part of a tool downstream from the digital content creation tool, the next time the artist goes to export from Blender, they may overwrite that change unless you've worked with them to make sure they incorporate it into their workflow. The other new node here you'll notice is the scene builder node. The asset processor itself doesn't actually convert source assets to product assets. The asset processor knows what asset builders exist and it has them do the work. This is done to make the pipeline modular. This means you can put the entirety of the logic for how a file is processed into a gem. In this case, the scene builder itself is in a gem. If you disable that module, you disable the whole builder, but you don't turn off the rest of the asset pipeline. So the scene builder processes the FBX files here, which we're going to zoom in now next to take a look at what that looks like. The entry point here is the process jobs. This is when the job has been created. The scene builder is going to do the work of creating the product assets. And just like the asset processor, the scene builder itself is modular because other gems, other systems are going to want to get involved. The rendering team, for example, didn't want to have to go into the scene builder code to change how the models and materials are generated from the source scene file. Instead, they wanted to be able to write that code in their own gem, which was really useful as we were spinning up this new renderer. We had the old renderer running side by side, and you could turn on and off either of them, run either of the renderers to get your work done as systems came online. This is also true of physics and any other modules that want to make use of this, including your own. If you have anything you want to pull out of the scene pipeline yourself, you can register just like physics, just like the Atom renderer does, listen to these events, respond to them, and create the output you need. The first set of steps here, you'll notice the pre-import and import event, and then we load the scene from file into the SDK format. Like I said earlier, we use a external SDK, the Open Asset Importer library, to load these scene files for us. This was done because it supports a huge number of scene file formats, and we've had a lot of requests over the years for support for different scene files based on teams' needs and preferences. So our thought was, if we go with something that is supports multiple formats, then we can let teams kind of control that themselves. The next step here is then that scene file is converted in memory from that SDK format scene to the O3DE format scene. This is done for a couple reasons. The first is portability. When we swapped from our previous SDK for loading and parsing FBX files to the new Open Asset Importer library, we foresaw that maybe other teams would have a similar need in the future. They might want to use a different library, as well as other teams may want to inject their own importer. They may want to use a different one either alongside or instead of. So this conversion process means that as long as you get the scene into the O3DE format, you don't need to, the rest of the pipeline after that doesn't need to worry how it got there. And same with beforehand. You can write a tool that converts and outputs to this format from whatever input you want. The other reason we did this was it was simple. We didn't have to change any of that already existing downstream code that was working with the scene in O3DE format. The next couple steps here are a couple more events to let the other systems know that how the scene file is coming along and processing, with the update manifest event being kind of the least instantly understandable. The scene manifest controls the scene settings that from generally the export steps are going to make use of to figure out how to convert that scene in the O3DE format to those product assets like the AZ model. And this event is one of the steps that makes sure that the manifest that contains the scene settings is ready to go and updated. It's a chance for other tools, including the Python integration, to respond to this message and adjust or make changes to the manifest as needed. And then finally, the export step. This is where the other listeners to these events can generate the product assets. So if you turned off the Atom gem, if you turned off the physics gem, if you turned off the animation gem, you wouldn't get a lot of product assets, if any, because the work of creating them is done in those other modules responding to these events. And you have a trio of events here, the pre-export, the export, and the post-export. This gives you a chance to do some controlling of order of operations if you need to run some logic before or after other products are generated, or you need to put things together at like finalized information after the product assets are generated. Maybe you need information from one product asset, they may not be ready to go. Then the post-export event and the pre-export event give you tools to manage that. Now that I've covered the scene builder, which controls how the scene files are processed from portable scene file formats like FBX into the product assets that are usable in the editor to build your game. Next, I'm going to explain the settings that control that process. Scene settings are used to control how those scene files are parsed and how the product assets are generated. This is done, a simple example of why you might want to do this is if you have a scene file with multiple meshes, for example, the scene earlier with the cube and the sphere, do you want those to come in as one AZ model welded together, or do you want the meshes kept separately? This is a setting that you can control with the scene settings at various steps in the process. The default logic may not always be what you want, which is why these settings need to be made available. I'm going to start by showing off the user interface for the graphical tool for editing scene settings. This is a good way to learn what settings are available to you for a scene file. Note that these tabs, like the meshes, actors, physics tabs, there's also an animation tab. These don't show up unless that information is in the scene file that you've opened to process. So this Sponza.fbx that's in the automated testing project does not have any animations associated with it. You'll see here that this is the default logic. If I've made no changes to the Sponza scene, I just loaded this in the tool, and it will, by default, weld every mesh from the scene into one mesh that can be placed and interacted with. Scene settings live in several places. That tool is just one place to view and edit these settings. So by default, there is a scene manifest that can live next to the scene file on disk. So if I have sponza.fbx, like we saw in the last scene, I'll have sponza.fbx.assetinfo that'll store the scene settings for sponza.fbx. This file can be generated using that scene settings tool. That scene settings tool will load this file, write changes to it, and store them when you finish editing. Or you can use upstream tools to edit and write that outside of that tool. The next place that scene settings are applied is the Python Asset Builder. This is a builder that can run before the scene builder itself. This was provided as an entry point for technical artists and other people who want to work in Python to manage the scene settings for a scene file. This will create a procedural scene file in the asset cache where product assets are, so that this is a product asset scene manifest that the scene builder will then later use if available. One of the differences here is that procedural scene manifest is not going to be writable besides from that tool. So if you have settings you want to let your content creators configure, then you might not want to make use of that. But if you have a lot of files that you want to apply settings to procedurally, or you want to prevent content creators from making changes, the procedural scene manifest is a great way to do that. And then finally, during the scene builder itself, there are callbacks that occur, like we saw in the scene builder walkthrough a little bit ago, that the scene manifest can be modified, applied, adjusted based on your needs. The final topic I want to cover is automation, options for technical artists and engineers to save content creators time and steps by automating steps in their workflow. At a high level, here's what that workflow looks like for content creation. You start with the digital content creation tool like Blender, Max, or Maya. Export to a portable format like FBX. Then the asset processor picks that file, newly modified file or new file, as well as the scene manifest, has any pre-scene builders run on it, like the Python Asset Builder. And then the scene builder itself processes it, creates the product assets for the editor, and then finally, content creators load up the editor and place the content into it in prefabs or in other ways. The first couple options for automation are at that first step, the pre-export and export step. A lot of teams in their digital content creation tool build themselves or make use of automation tools to pre-check content for any known issues to save time later, as well as prep and make final changes to the content before it's written to the scene file. The next step from here is the scene manifest itself. It's now in a JSON format that's built to be more easily read and written, both manually as well as from external tools. So that custom export script could write to this, or other tools could read and write to the scene manifest to make changes to prep that FBX file for processing later. After that, there are builders that can be set up to run before the scene builder itself. There's already an existing one, the Python Asset Builder, that provides a Python entry point to generate manifests at build time for processing those FBX files. So this is a good place for technical artists who might already have an idea of how they want that content to be processed to write a custom builder or a custom scene manifest from this builder. Then the scene builder itself has those C++ and Python callbacks I covered earlier. So depending on how things are set up in the process, this might make the most sense for your team, especially if you have engineers who want to work in C++. The procedural prefabs are generated at this step if you need an example to look at. Finally, the editor itself has support for automation, especially with Python. This is a good place to automate any final steps, putting that content together, gathering the pieces, and placing them into a scene in the way that makes sense for how that content was built. So to wrap things up, I've given you a walkthrough of the scene pipeline and covered what scene files are, how they're processed, and what they're processed into. Then the scene settings themselves that control how those scene files are processed to make sure you get the content into the engine the way you want. And then finally, options you have for automating workflows to make it so the content you get into the engine matches your needs. And here are some documentation links and further reading, including the open asset importer library we make use of, the asset builder information, and scene settings. Thanks for attending my talk, and I'll be available for Q&A in Discord after this finishes.